All right, welcome to another video on interface performance for drivers. Um, yes, so why am I doing this video? Because I got asked a question on the TinyGo Slack channel about why was a certain usage faster, a certain pattern faster than another. In particular, it was about using generics for, driver design. So, and I wanted to dive in a little bit and share my knowledge. So, poop. No, whoops. Uh, yeah. So this is what I've got prepared today to talk about. I was hoping it might be a short video. Let's make that bigger. All right, let's go. Where do we use interface in... Oh, yeah, I've been looking a bit. When do we use interface in driver development? So I think the best example of that is the drivers repo, unsurprisingly. We have the I2C, I squared C interface, if you will. I2C, blah, blah, blah. Look, it's got one method. And it describes the I squared C protocol almost in full, good enough for like 99% of cases. We do a transmit to an address with a write buffer, the bytes we're going to write at the start in write mode, and then the bytes we are going to read after we stop sending those write bytes. Sometimes this is nil or zero length. Sometimes this is 0 or nil length. So more to read here. Then there's a SPI. You've got the transfer. SPI is basically this. You don't really need this method except for those 1% of cases. But yeah, SPI usually since it's full duplex, all you do is write a set of bytes and read a set of bytes, same length. Both of these buffers have to be the same length, unless you plan on not writing or not reading any bytes, in which case you can pass in a nil buffer to either one of these. It's described here in the documentation. Transfer is basically just the single byte implementation of TX. So really, you could implement a function that does transfer by just reading and writing a single byte using TX. And so, yeah, really interesting stuff here. Like interfaces that describe protocols with a single method. My kind of jam. So let's jump over to interfaces versus static calls. What do I mean by a static call versus an interface? Well, I guess it's time to bring up a program. Let's make a new main.go here. Okay, so this is just a random. Fine. So imagine you have your func main here. Func main will call another function, add A and B. I'm kind of doing this off the cuff, so don't really have anything planned. A is equal to add 1, 2. Print ln A. So that's a static call. And then we can also have an interface, which does pretty much the same work. I have to just an empty struct, I guess. And if we read oh, that's odd. Expected time. Oh, func. Return a. So we can agree these two functions do exactly the same thing. When we do add with interface adder, and we do a, b, int. So I'm going through extraordinary lengths just to demonstrate is an adder that adder dot add ab. So yeah, this is not the way we. So what I mean is this is an interface call. If we do an adder implementation. Wow, so I went through all this to just show this, I guess. An adder 1, 2. I feel like this maybe wasn't worth all the effort, but hey, worth, I guess being explicit is good. This is an interface, a static call, because the compiler can deduce what function is being called and just directly call that address. And this is a function call, which is also static, but the non-static part of the function, the interface call, which I'm referring to, is this, right? This is also a function call. This is actually technically will be a static call in the code, but it's not going to be a call to this method, right? We're going to have some overhead in between, and the overhead really depends on the compiler details, or compiler / runtime details. TinyGo kind of inserts its own code inside here, so this will almost exclusively be slower than this just simple function call, since it can be optimized in certain cases. I think in this case, I believe TinyGo can optimize this. It can deduce, okay, this is just a pure function, boom, boom, oh, it just calls this. TinyGo might be able to optimize this, but this is not the case for when designing drivers. Like, for example, the drivers repo I was just showing you. These types are used in contexts where the compiler might have a harder time inferencing, and that'll be I guess that'll be shown in full when I show benchmarks. Not too many benchmarks, but just enough to give you an idea. I just wanted to put in a short video for this. So yeah, this is actually a static call to a runtime function that's called like runtime get method, and then call that method. And what TinyGo does underneath the hood is actually search every implementation that exists of adder. So if maybe there was another adder implementation too, it searched every implementation to see, hey, searches all their methods. Or no, searches for every single implementation. Oh, it has a for loop somewhere. So currently, this is today. This might change in the future, but currently it searches every single type to see if it matches. So we'll see more about that on the benchmark. So I think that's enough to describe the differences between static function call and an interface, a virtual method call. Let's continue. Static call is our base speed. So like I said, this is like the most basic, like this is the overhead of a single function call is like the slowest the function can be, and this function is going to be like, I guess, what the operations it takes for the function overhead setup plus one cycle, right? Add is one cycle on most CPUs. This can furthermore, I mean, there's the details of the compiler as well. Compilers can optimize this, inline this. This could be inlined right here. So it doesn't even have the overhead of the function call setup. So it's actually even faster than a static call, which I was speaking of before. And what's more, the compiler can even optimize this to just a constant, just straight up, just directly. It doesn't even do anything in this line. It just prints 3 here. This most likely will be optimized to as just a constant at compile time. So there's a lot of minutiae to like actually benchmarking and stuff. That's why I really didn't want to write a benchmark for this, because it's really hard to benchmark this without getting something wrong in between, like now with the new benchmark API benchmark b.loop, that's gonna be easier. Test like benchmark function does b.loop. I don't have the latest version of Go to show you what I mean, but there is a new b.loop. Oh. Okay, for b.loop, code to measure. So this is the new API. Why wasn't it showing up in IntelliSense? I don't know. Okay, so use this if you want a benchmark. But then again, I can't do that because TinyGo, I don't know if it supports it, and I'm mostly interested in testing this in an embedded environment, and I'll show you benchmarks in an embedded environment afterwards. So that's that. Why our interface is slightly slower? Well, it's a virtual method call. TinyGo currently searches every implementation, in the for loop. Interface calls can actually be much slower in certain cases. Yeah, that's because of it's a virtual method call. If the compiler isn't aware that there's only one implementation that can possibly be used, it's going to be certainly going to be a virtual method call. Otherwise, it might be just a dynamic call. And that brings us to dynamic functions. What do I mean by a dynamic call? Well, something like this. Maybe we have a driver. Now let's just straight up show you what I mean by dynamic call. So the callback. So usually we talk about callbacks. Return a plus b, and maybe it's just so we can talk about something that's not optimized by the compiler. Add with dynamic call. func int a b int return adder ab. So this is yet another way to do the same work, right? And this is, you don't often see this in drivers. People don't use callbacks for, function types for the hardware abstraction layer. Though there is a case, I'm making a case for a new hardware abstraction layer for the pin type, which does use these, and there's reasons for that. We'll look at the PR at the end. But yeah, so dynamic calls are, in my understanding, slower than static calls. Just because I'm not sure why. I feel like the only reason they're slower is because the compiler can't optimize them. Because really, if it's just calling the or maybe it's due to like loading, like how the CPU loads memory, executable memory. Maybe like, oh, I can load all these functions together because I know that this function is going to be close to this one. But yeah, my knowledge, I did not prepare this video, so I can't tell you why dynamic calls are sometimes always slower than static calls. I guess look that up. Hey, we have AI. Why are dynamic calls slower than static calls? I don't think it does not require. Okay. Don't think I understand that. Dynamic calls or runtime resolution. Okay. I think it does have something to do with, oh, look, this can be loaded together. Like these functions are static in my program, and I know that if I load this function, I'm going to have to call this function. So I load them into the CPU cache. Although like in embedded systems, the CPU cache isn't that much, so maybe it doesn't matter on embedded systems. The compiler with the function location is not known. The call is resolved at runtime. Okay, a table. Okay, that's new to me. Let's continue. When in doubt, just bug out. How generics can be faster. Let's just end with that point with, it's slower, and we'll see an example of in cases where we'd want to use it. How generics can be faster. Yes, this was the question on the TinyGo Slack channel. Why would you want to use generics to make your program faster? Well, we just saw our adder implementation. Like when we have an interface, TinyGo has to resolve, hey, what type is this? Well, what are these types? This type. What are this type's methods? Because I need to know which add to call. Do I have to call like this add? Do I have to call this add? So there is like almost certainly a for loop somewhere, or a map that where TinyGo has to ask, hey, are you this type? No. Are you this type? Oh yes, you are this type because your type signature matches. So it's gonna call type signature. That's not even a thing, right? But yeah, you're this type. So I'm gonna call this method here. I hope that's. Oh my god! I just realized that I could make this bigger. So yeah, runtime resolution of interfaces is slow. How can we fix that with generics? The answer is just generify your function or driver type. So here we have add with generics. And what we're going to do, adder, a adder, a b int. Check this out. Adder. Okay, so haha. So what do we have here? It's pretty much the same exact code as add with interface, except I just added a generic type parameter list to my function. It's just same function, just added this and modified the type of adder to be generic. So adder is a generic type. It's not an interface type anymore. And so the compiler, when it resolves something like this, adder add with generics, look, it looks exactly the same, and code will most of the time look exactly the same with generics because it inferences the type. At compile time, this type is known. The compiler can tell what type is here at compile time and can therefore just straight up call this function. So this just add with generics really behaves much more similar to a static call than it does to an interface call. Just because the compiler has more information. You've given the compiler this type hint, which it can use. It's even it's going to be faster than the dynamic calls due to what we just saw here, which I didn't really understand. But yeah, dynamic resolution runtime, like everything's happening at compile time. I think we can agree with Search Labs here. Like this is solving stuff at compile time that lets us know exactly. Look, it even tells us. Look, this is. Oh no, sorry. Yeah, it solves stuff at compile time. Basically, that's the magic of generics. A little caveat: we don't use generics in our TinyGo drivers. Just because the added performance benefit is just not worth it. I mean, look at these methods. You're passing in this does a bunch of work beneath. It sets up the registers needed to transmit to a certain address. It then starts sending out those bytes, and most of the time we don't have DMA implemented for these methods. So it's just gonna do a loop and send a byte at a time and sleep in between. Not sleep, but it's gonna yield to the runtime. And so this is gonna be just orders and orders of magnitude slower than a static call. Not to mention even a interface call, a virtual method call. That's gonna be so much slower than that. So we don't really care about performance. The last bit of performance you can get out of, do I use interfaces or do I use a callback with a dynamic call to not undergo the overhead of the virtual method call. And virtual method calls are something that it's not even slow today. You get the same performance as a dynamic call in most cases. Again, we'll see about that in the benchmarks. So generics, is it worth it? I think not, unless you're really looking for that extra bit of performance. And if you really are looking for that that bit of performance that generics over interfaces uses, you're going to want to maybe not even look at other options. More on that right now. So is it worth the code complexity? Check. Like, I guess we'll see. Let's look at the drivers.pin discussion. So this is a pull request that my good friend that program submitted here. So there is, so this is, let's put this. If you want to follow along, I'll put this in the. I'm gonna call it show notes because I watch a lot of podcasts, but it would be the video description, I guess. So yes, if you want to follow along, check the video description. But really, we had this very fruitful and just great conversation on how to design one of the simplest hardware abstraction layers, the pin HAL. And just because there's so much nuances about how people use this, so I guess the simplest answer would be just, let's just use interfaces because that's what we've always been doing. I a few years ago had gone the interface route and found that, hey, I'm really worried about performance when using a pin because the overhead is non-negligible compared to what the function actually does, right? For a pin, if you're using like a pin that is on your microcontroller, like one of your GPIOs, I mean, that's going to be what, like 3 cycles, 4 or 5 cycles at most. So everything you do, like even the function setup overhead, like everything matters in that case. In most cases, where pins are actually being used, it doesn't matter because people are using it to control the SPI chip select pin. So SPI usually, chip select. So for SPI, you usually have like the data pins, and then you have the chip select pin, which you just toggle on and off when you're sending bytes. So usually it's off. It's off when bytes are being sent, and then after you're done sending to that server or that peripheral, you put the pin in high back on again. So for this case, you don't really care about like if your pin hardware abstraction layer is slow, because this is orders of magnitude slower. Even if you're doing DMA and squeezing the performance out of this, you're still like doing a bunch of stuff in here. So this you don't care about pin. So most people using drivers in TinyGo really hadn't ever run into the problem of a slow pin hardware abstraction layer. I had used pins for controlling motors, where every pulse of a pin is a step in the motor. So, the pin hardware abstraction layer is just 20 nanoseconds slower. Who cares? But I would care a lot, because that would mean my motor's maximum speed would be 50% of what it could be, half as fast, because maybe the base speed, maybe if you use generics, maybe it was 10 nanoseconds. So there are cases where the pin hardware abstraction layer is actually you want to have it be fast for like bit banging protocols. There's a bunch of reasons, and I think I've listed them here. And blah blah blah. So benchmarks, I guess, is, you know, let's show you the money. So I wrote a benchmark for actually like checking out, hey, how slow can a interface compare to a dynamic function call be? Because I've been proposing using this instead of an interface, using function types. Just like we saw, the dynamic call or callback, as you will. These are not all of the pros. I did find several more, which I talked about here. So really a lot of pros to using this, and I think we agreed on at least giving it a test run. You know, writing another PR. And I think I've. So I was talking about the benchmarks, and this benchmark turned out to be blah blah blah. Here's the results of the benchmark. So so you'll notice the dynamic call is pretty much the same speed. It gets actually faster, but that's it's 10 microseconds faster, but that's a artifact of the benchmark. Same here, according to Ike. This is an artifact. It should be this. It's going to be around the same speed. This must be due to a weird CPU low-level stuff. But yeah, you can see it runs around 70 nanoseconds, the speed of a single interface implementation versus a dynamic call. And then as you start adding pin implementations, it actually gets much slower. And not only like it's not 2 times as slow, it can, like, every pin implementation slows. First it slows down like times 3, right? So this is times 3 slower. So if you're using the pin HAL to like control a motor, it's gonna be 3 times as slow. And then when you add one more pin implementation, it gets even slower. So this was an issue I raised. Hey, we're gonna we're gonna be our SPI implementations are gonna be fine, but hey, we're really like negatively impacting our future users of TinyGo, which really need a fast pin hardware abstraction layer. And yeah, I think we talked about it, and we agreed we're gonna look at other options, and that's why I think there's another PR somewhere here. The driver's pin. There's this PR. Ike is on vacations, so still hasn't responded, but yeah, maybe we do this. So yeah, I think that's all for today. I answered this question by saying basically, yeah, pins need the speed because the actual function call of high or low, set true, set false, is a few nanoseconds. So really, like every nanosecond counts in that case, unlike SPI TX and I2C TX and most other drivers. So yes, that's all for today. Thank you for watching, and I hope you enjoyed. Hope it was useful. Bye bye.